Okay, so welcome back. It's Wednesday, December the 9th. We're doing more volumes of revolution. Consider 83AB4, which says, the figure above shows the graph of the equation rad x plus rad y is 2. Let R be the shaded region. It's not shaded, whatever, between the graph, the x-axis from 0 to 1. Okay, so we're only dealing from 0 to 1. All right, now part A we did already, find the area. Part B, set up but do not integrate an integral expression. I don't know, look in your notes. Set up but do not integrate an integral expression in terms of a single variable for the volume of the solid generated when you revolve the region R about the x-axis. Okay, well, let's draw stuff. It's always easy to see if you draw stuff. Okay? So remember the asterisk goes through 0, 4 and 4, 0. These are intercepts, x and y intercepts. It looks almost like a hyperbola.
What's the answer for that?
I don't know. Look at your notes. Okay, I'm not doing that right now. Okay, get the notes at another time. Thank you. Okay, so the region is from 0 to 1. Okay? Now last time we did vertical strips. And I'm not sure if we did it right. I think we went from 0 to 4 by accident, didn't we? Or did we? I don't know. Anyway, from 0 to 1. And if we do vertical strips, let's do some vertical strips. Vertical Riemann rectangles. Let's say like that. Okay. Again, what is the thickness? How wide is this thing? Dx, good. What's the height? It's the function value. That's a y, right? We got to get y alone here, don't we? That's what we did to find the area. But now I'm revolving around the x-axis. Now notice that the strip is perpendicular to the axis of rotation, and it touches the axis of rotation, right? So that means we can do a disk. How do you set up a disk? The volume about the x-axis is what? Pi, the integral from 0 to 1 if we're doing a function in x, times what? The radius squared times the thickness. Well, what's the radius squared? I don't know, we got to find out. How do you get y alone? Okay, so y is 2 minus rad y. And, I'm sorry, not y. I'm trying to... Okay, rad y alone is 2 minus rad x. So I want to get y. And so square both sides, so y is 2 minus rad x squared. But remember we said that the y value is the radius, so what are you going to do with this? Square it, so it's 2 minus rad x to the 4th. Notice that's why they told you not to integrate it. Not because you can't, but because it just takes a lot of time to FOIL a whole ton of times, okay? Because this isn't a use of, this is FOIL 3 times. Well, it's not really FOIL. It's distributing 3 times, right? A binomial over a binomial, and a binomial over a trinomial, and a binomial over a quadrinomial. Ugh, what a mess. But we can ask Hal for an answer, can't we? Let's ask Hal. Let's see, what does Hal say about this? All right, let's bring Hal over here. And let's turn that off. Turn that off. Okay. All right, Hal, earn your keep, will you? Let's see. This is getting a little too big here. Hang on. It's a little bit smaller, bring it down. Okay, so I'm going to just clear this and clear that and go, let's see, pi is second caret is pi, right? Whoops, clear that. Second caret is pi. And then second 7 for the integral. And we're going to take the quantity 2 minus rad, where's rad over here, right? Second this, x. That quantity is being raised to the 4th power. With respect to x from 0 to 4. No, to 1 we said, right? All right, and so what do we get? There's a decimal equivalent. I could probably get an exact answer to this. The mode, what mode am I in? Am I in the prox mode? Yeah, that's why. Let me go to auto mode, see if there's an exact answer. There should be, because I think it's integrable, so you could do this algebraically. There you go. Why? Because the antiderivative can be done, it's just a mess. It's this. Okay, and yeah, to do that, it just involves a lot of foiling, and we're not going to spend time on that right now. Part C involves an integration technique we're going to talk about next week. All right, or volume technique we're going to talk about next week. So don't worry about C, we'll come back to it. How about this? Any questions on that one? Just setting it up, that's all we wanted. Set up a disk, is that okay? All right. How about this question? Can I find the volume of a cone, any cone, this way? Let's see, how about this? Let's draw a line. Here's my line. Well, actually, I'll do it this way. So there's my line. Here's the origin, here's the x-axis. Let's say the line has an x-intercept of r, so this point is r comma 0, and a y-intercept of h, so this point is 0 comma h. And if you take this triangular region and revolve it around the y-axis, don't you get a cone? With a height h and a radius r? Ooh, sneaky. So, how do I set up a volume about the y-axis with this line revolving on the y-axis? Victor has a suggestion? Or are you just stretching? Okay, what? I'm going to go around y, so it'll be a function in y from 0 to h. That's a good point, okay. So then what kind of strips am I talking about? Horizontal or vertical? Horizontal. All right, let's draw some horizontal strips. Say like this. In other words, a Riemann rectangle, right? Okay. Now, if I take that Riemann rectangle and I revolve it on the y-axis, it sweeps out a disk, right? It's a very short cylinder. Okay, its thickness is what? dy now, right? Okay. And this value isn't at the radius of rotation. Remember, when the strip is perpendicular to the axis of rotation and touches it, that's when you do disks. We're eventually going to be doing disks, washers, shells, and something else when it's not a revolution. I'm going to be having 4 different kinds of volume problems. All right, so yeah.
Can you ever revolve around a line that's not horizontal?
Yeah, that's not part of this curriculum, but you can. They will ask you to revolve around horizontal and vertical lines. It's sort of a pain to do it off like a diagonal line unless you change your axes, like to polar mode or something. Okay, so we're not really going to touch that until we come back to polar mode. So we have to have this function. Do you know how to write the equation of this line? Y minus y1 equals m times x minus x1, right? All right, now what's x1, y1? Well, pick any point you like. You got 2 points. You got 0h and you get r0. Which point would you like? R0? Okay, so y minus 0 equals m times x minus r. Okay, now what's m? Delta y over delta x. Down h over r. So negative h over r. Right? So there you go. There's y. But is that what you wanted? No, we really wanted a function in x because we're revolving around the y-axis, so we need dy's and functions in y's. And so can we solve this for x? All right, what are you going to do? And easier not to distribute. Get rid of negative h over r by dividing. How do you divide by a fraction? You multiply by it. So negative r over hy equals x minus r. So what's x? Plus r, right. So I'm going to write it this way. X equals r minus r over hy. Okay, so there's my function of y that represents this line in terms of y, okay? Now, that x value isn't at the radius of rotation, right? So let's set up a disk problem. Okay, the volume about the y-axis is going to be, how do you set it up? Pi, the integral from 0 to h of r minus r over h times y squared dy. Okay, now we can square this. That's just a FOIL problem. That's not too bad. That's like the previous example. So let's do it. Let's see. Let me get some room here. How are we going to square that out? Well, let's see. R squared r times negative rhy is negative r squared h over y. We're going to get two of those. Plus r squared over h squared y squared. And if you need to do FOIL on the side, scratch paper, go for it. I think that's correct. We didn't integrate yet. We're just setting it up so we can. All right, so integrate. And if you say r cubed over 3, I have to get up and smack you. R cubed x? No. R squared x. Well, it was close. It wasn't that bad. They we're missing the over 3. Well, it's over y, yeah. Okay, good. Minus 2r squared h, what? Y squared over 2. Well, the 2's cancel then, don't they? Hello. All right, so there's a minus. All right, and plus r squared over h squared times y cubed over 3. Good. Okay, we're going to evaluate this using the first fundamental theorem of calculus from 0 to h. Don't forget the pi multiplies that answer. And if you plug in 0, does it drop out? It does. Check. Be careful. It doesn't always drop out. Plug in h, what do you get? Well, let's see. Pi times r squared h minus r squared h squared over h plus r squared h cubed over h squared cubed, over 3, sorry. Well, apparently that's the volume of a cone. But we can simplify it, can't we? Let's see. How are we going to simplify this? Well, h into h squared is what? H. So we get pi r squared h minus r squared h. Oh, that's convenient. And h squared into h cubed is h plus r squared h over 3. And so, what's the final answer, Regis?
R squared h over 3.
Pi r squared h over 3. Didn't we say earlier in the year the volume of a cone is 1/3 the volume of a cylinder? Like a Coke can? Remember the Coke can problem? And the volume of a Coke can is the area of the base, pi r squared, a circle, times the height. Yeah, that's it. The volume of a cone. Ta-da! There you go. Wasn't that special? Okay, that's a famous result. All your volume formulas, all your area formulas originally came from integration. Okay, any questions up to here? Okay, how about we try one more like that? Let's see. Let's say I give you y equals rad x, and I want the region bounded by the x-axis from 0 to 4 in x, and I want to find the volume of revolution about the y-axis. That's the question. Okay, and we've seen this graph before, but we didn't ask the same question yet. So let's see. Let's graph this. It's always nice to see what you're doing. Y equals rad x, right? From 0 to 4 in x. So I'm talking about the region bounded by the curve and the x-axis from 0 to 4, this region. But what if I revolve this about the y-axis? Now this is already hinting at a new method, because if you do vertical strips and revolve them around the y-axis, it's not a disk, because the vertical strips would be parallel to the axis of rotation. That's something new we got to talk about. Or if you do horizontal strips, they're perpendicular to the axis of rotation, but there's a hole in the middle. That's different too. But it's not that different. You could take the big disk, using this as your function, minus a little disk, pretend that the hole has volume, and subtract, right? So this is called washers. If I do this in horizontal strips, it's a big disk minus a little disk. So it's not really that different. It's just that the strip doesn't touch the axis of rotation, all right? So if I revolve this around, there's going to be a hole in my disk. I'm going to call that a washer, right? Okay, like they have washers in plumbing, right? Okay. But it's very simple. Pretend that this does touch the y-axis, and do one humongous disk. In this case, with a constant x value, is going to be a real cylinder. That's what it is, right? But then then you have this inner disk that's missing, gets smaller and smaller here, bigger and bigger out here, right? We're going to subtract that away. So it's big disk minus little disk is all it is. So we're going to set up the volume about the y-axis is going to be pi, the integral from, well, I'm not going to say what yet. Well, because I'm doing it in y, it's not 0 to 4. What is it? 0 to 2, isn't it? Square root of 4.
2, yeah.
So 0 to 2. It's going from 0 to 2 of big R squared dy minus little r squared dy. So it's just the big disk minus little disk. That's all it is. Now, what is this function here?
4.
X equals 4. That's already x equals, right? Don't we need x equals? Okay, because the radius is in terms of x. How do you get x alone here? Square it. So x equals y squared. Now, who's the bigger radius? From the y-axis, who's farther? X equals 4 or x equals y squared? So the big disk is based on 4 and the little disk is based on y squared. All right, so there it is. We're done. That's the setup. It equals pi, the integral from 0 to 2 of 4 squared. Okay. I'll leave it at that. Minus this. And we'll continue with washers tomorrow. Okay, let's save this stuff.